Finding the maxima and minima of functions is a super important application. Pretty much all problems in real life involve those of finding maxes and mins. Unfortunately, to start off though, we're going to have to look at this big wall of text, because there's a few things that we need to define. First, we say that a point C is a local maximum of a function f if it's bigger than everything nearby. The way that we say nearby in math is to say that f of x is less than or equal to f of c for all x in an interval containing c. If we flip that inequality so that f of x is greater than or equal to c, that gives us the notion of a local minimum. But we're usually more interested in the big picture. What are the largest and smallest values of a function on its entire domain? To that end, a local maximum is the global maximum, sometimes called an absolute maximum, if it is at least as big as anything else in the domain of f. Of course, there's a corresponding notion for the global minimum as well. Let's draw a generic function to get an idea of what this looks like. I'm going to label in green those points which correspond to maxes and mins. I've excluded the word local, but it's implied. Again, notice that a local max only needs to be bigger than everything nearby it, and same with a local min. And when a max or min is the absolute largest or smallest value of the function, we give it the special distinction of being a global extrema. And if we stare at this graph a bit, do you see how the maxes and mins always occur where the tangent line is horizontal? This suggests that we might be able to use derivatives to help us find these points. Indeed, if f is a function and you are given a maximum or minimum of that function, you can be guaranteed that that point corresponds to a critical point of f. So that's great. If we find the critical points of a function, we have candidates for the maxima and minima. However, not every critical point has to be an extremum. For example, take the function x cubed, whose derivative is 3x squared. X equals 0 is definitely a critical point of f. However, if we look at the graph of f at the point 0, we see that even though the tangent line is horizontal, x equals 0 is neither a maximum nor minimum of f. What about critical points where the derivative doesn't exist? For example, something like 1 over x squared, whose derivative is negative 2 over x cubed. Here again, x equals 0 is a critical point, but the function isn't even defined at 0. So this point couldn't possibly be an extremum of f. Okay, so we find our critical points, but we have no idea if these points are maxes, mins, or neither. So what do we do? If you look back at our generic function above, you might notice that our function changes from increasing to decreasing, and vice versa, at maxima and minima. So maybe we can use derivatives again in order to help us. Let's suppose then that c is a critical point of the function f. If f is increasing just to the left of c and decreasing just to the right of c, then c must be a maximum. This is easy to remember. Just draw a picture of something that goes from increasing to decreasing, and yep, that's a max. As usual, we flip this around as well, so that if f is decreasing just to the left of c and increasing just to the right of c, then c is a minimum. Again, drawing a picture makes it clear that this is true. So let's try this out on a function. Let's find and classify the critical points of the function x squared over x plus 1 squared. I'm going to let you compute this derivative, so check that it's 2x over x plus 1 cubed. The critical points can then be read off as x equals negative 1, where the denominator is 0, and x equals 0, where the numerator is 0. However, x equals negative 1 cannot be a max or min, since the function isn't even defined there. I'm going to include it in our work below, but just keep in mind that it's not a candidate. To see if f is increasing or decreasing near our critical point, we're going to need to check the sign of f prime. I'll use a table to do this, and I'm going to break down f prime into its pieces to make it a little bit easier to do. Checking the signs of these component functions on each of the intervals gives us this, so that the sign of f prime is as follows. Looking at our critical point x equals 0, we see that we're decreasing to the left and that we're increasing to the right. So, by our theorem, we can conclude that x equals 0 is a minimum. Okay, so finding maxima and minima has historically been something that's actually been really tough. The fact that we can now use calculus to help adds a lot of strength to our toolbox.